All right, we'll start. Okay, so before I talk about today's topic, I want to first elaborate one of the questions from Campus Wire. So it's regarding the first homework problem where you are asked to simplify a function to use the symptotic notations. And the question is regarding constants, okay? In some sense, we said in class that, okay, big theta notation, ignore constants. Okay, now note that when we say that it's ignore constant, it's ignoring the constant in the multiplicative factor or when you add something. Okay, so for example, what I mean is that if you have 3n, just annotate, you have a 3n squared, then this is a multiplicative constant. And by definition of the big theta notation, we can ignore that because the definition of big theta is that f of n is smaller than c1 g of n, bigger than c2 g of n. So this is a multiplicative constant, okay? However, if you have constant in the exponent, then you have to think, what does that mean, okay? So for example, if I have 3 to the power of n and 3 to the power of 2n, it looks like, okay, we only differ by a constant, okay? However, what is the, here, if you think, what is 3? So this is our f of n, and this is our g of n, okay? So what is 3 to the power of gn? This is in fact 3n squared, namely 3n to the power of 2, okay? While this is just a single 3 of n. So as we can see, the second function g of n is significantly larger. So this is not in the big theta of this, okay? Another way to see this is that if I use the limit notation, then 3n divided over 3 2n equal to 1 over 3n equal to 0, which means that f of n, 3 to the power of n, is far smaller than g of n. Okay, so the exponent in the constant in the exponent, you have to be very careful. Okay, now for the logarithmic, on the other hand, I mentioned last time that we have log a of n and the log b of n are always big theta notation as long as a, b are bigger than 1. Okay, so this is not because that they are constant, it's because that by using the change of base formula, this equal to, so log and a equal to, which is in other words, the first function f of n equal to a constant times the second function g of n. That's why this two have a big theta notation. Okay, in your homework, now, even though sometimes we write just log n, but really log n means that I am assuming to have 10 as the base. Okay, so in the homework, if you write log n base 2, that's also okay. Okay, although it will not be okay if you say, oh, the answer is the following. If you say the answer, you give me a notation like log n of base 2 plus log n base 3. Now, this is not the most simplest form. Okay, this you can either write, or you can simply write this is the same as log n. Note that when I write log n, I'm really assuming base 10. Okay. All right, so I hope this clarified one of the homework problem. Okay, so last time we looked at the worst and the best case, okay? And then we said that, okay, in practice, sometimes both worst case and the best case can be caused by some specific input, which may not be frequent, okay? So it makes sense that to talk about the average, the expected time complexity. Okay. And what we did last time is that we distinguished actually when we talk about the expected or average running time, okay, there are different models. One is that if I know what is the distribution of the input, so I know that the input type 1 going to 5 inputs are going to be like that, 10 inputs are going to be like input type 2, then I can average for each of the input, what is the running time, and then average it out. Okay, but this does assume that we know a distribution of the input. Okay, And we went through an example, this linear search, and we said that, okay, suppose as we assume that for your input, which is an array A with the key that you're looking for, we said that assume that the key you're looking for is equally likely to be any position in the array. Okay, under this assumption, so this gives you an assumption on the possible inputs. Okay, under this assumption, we said that since everything is equally likely, then the time, the average time is that the time for each type of input, okay, multiplied with the probability is happening, and the probability is 1/n, because each position is equally likely, and the expected running time in the end give us also set of n. Okay, and we also went through at the end of last class, we also look at another very artificial but very skilled distribution of input, and argue in that case the expected time is only order 1 if you assume that all input are the good case. Okay, so this depends on that we have a model of what the input is. Okay, now this is not always, we don't always have this prior information. We cannot always assume that we know what's the distribution of the input. Okay, so the randomized algorithm instead will have the randomness built inside the algorithm. Okay, there's some randomness in the algorithm. Okay, and as a result, number one, different from the probabilistic algorithm, for the same input, the running time is no longer fixed because of that. We're going to see an example in a minute, okay? But the good thing is that because of the randomness in the algorithm, you can argue, very often you can argue that, no, you cannot say, I'm going to come up with a really bad input, because even if your input is bad, because of the randomness in the algorithm, it may make it no longer bad, okay? So then you can talk about expected running time. You can talk about expected running time even when we run algorithm on a single input. Okay, so that's the distinction between these two. Okay, so on the high level, probabilistic analysis is say that if I know how the input is going to be like, what is the model of it, like what's a probability of each type of input, if we know that beforehand. Okay, randomizes that we don't assume anything on the input. Okay, but we're going to add some random bits in the algorithm. So let's look at an example to make this a bit more concrete. So we are now going to focus on analyzing the randomized algorithms, okay? So let's look at the following example. So here, this is just the same search problem. We're given the array A and the key K, and I want to see whether this key K is in the array or not, okay? The only difference is that before I do the search, look for the key, I first randomly permute the array. Okay, so what this function is doing is that it randomly, so what this function is doing is that it randomly permute array A. In other words, after I do this, any permutation of the all the numbers in A is equally likely. Okay, so every permutation of numbers in A is equally likely. Okay, so I randomly permute the array. Okay, then I go through this randomly permuted array and check whether X is in it, or check whether the key I'm looking for is in it or not. Okay, so this is the only modification. Okay, now I want to first, so before we talk about the expected case, okay, what is the worst case? Well, whatever, no matter how you permute the array, worst case, I'm just unlucky, the key I'm looking for happened to be the last one in the array, okay? Which means that we have to go through the entire for loops for n iteration. So the worst case, time remains theta of n, because I have to go through every element in A to see whether K is inside or not. Okay, so that doesn't change. Okay, so that's the first thing. Okay. The second thing I want you to notice is that, okay, so imagine my array, Okay, so a simple example. Imagine my array A is the input array A is 5, 3, 10, 9. Okay, and I'm running this algorithm to call and I'm looking for 10. Okay, now without the randomness in the previous linear search, that means that I have to go through the array step each position by position, and then in the third position I find 10. So then my time in that case is 3, assuming each operation takes unit time. Okay, so in the third position we find 10, then we return it. Okay, now with this randomized version, remember that the first step we first randomly permute A. Okay, so let's call this once, and when I randomly permute, it could be anything. Let's say that we got after I do the random after random shuffle, let's say that my A now becomes 3, 10, 9, 5. Okay, if this is the case, then when I run the algorithm, then 10 will be found in the second try. Okay, so after 2 steps, we found 10. Okay, okay. So if I random shuffle, in this case, it takes time too. Okay. However, now suppose that Alex comes and say, I'm going to run this again. When he ran it, the algorithm then would again do a random shuffle, but every time it may be different. So when Alex ran it, maybe the random shuffling returned by the algorithm will be 10, 5, 9, 3. In that case, he immediately found K. Okay, or maybe when Bob comes and then he's unlucky, 10 was the last one, so he has to search through everything. Okay, so what I'm saying is that even when you call the same algorithm on the same input, because the first step of your algorithm perform a random permutation. Okay, so even when you call down the same input, the running time is no longer the same. Okay, depending on how lucky you are. In this case, if your array size n, then after random permutation, the key you're looking for could be in any position. Okay, so it's important to first realize that the running time of the algorithm now is not deterministic anymore. Okay, so even on the same input. Okay, so every time your algorithm execute a little bit differently because of the randomness inside. Okay, all right, but still we can talk about what is expected time on this input. Okay, so now this is what we're going to find out. Okay, all right. So let's just make one simple assumption, means assume that we always look for keys that's already in A. So the key you're looking for is always already in the array. Okay. The key observation is that after this random shuffle, okay, your array become any random permutation is equally likely. Your key is fixed. You're looking for this key. Okay. Then after that, where can the key be in? Namely, which position can the key land up to? It turned out because everything is so uniform randomly, you shuffled it. So the key K is in the ith position, is equally likely to fall in any position in your array. Can be the first one, can be the second one, can be the third one, and so on after you randomly permute it. Okay, which means that the probability that the key falls in the ith position in our array is the same as any other position, which is 1 over n, because there are n choices. Okay, so this is a key observation. Okay, even for the same K. Okay, all right. Now, what is the expected running time? I often use ET to represent expected time. Okay, so expected running time, as we said earlier, is that you say, okay, what are the possible cases? Okay, so what is the time for each of the cases? Well, each of the cases means that the cases, the running time of this algorithm is different while K lands on a different position. So basically, for each possible position of the key, that's one case, okay? Now you want to sum up this and average it out. In other words, you need to multiply this with the probability that this case is happening. Okay, But then you need to check for all possible cases. Okay, all possible cases is that K could land at I equal to 0, 1, 2, 3 till n minus 1 position of the array. Okay, so this is expected running time. And since we already know this is 1 over n, okay, so this is the same. And what we did last time is that if the position, the key you're looking for is in the ith position, then you return after I iteration of the for loop because we found it, okay? Which means that the running time is C times I, okay? So this means that the expected running time equal to C over n sum of I, where I goes from 0 to n minus 1. And this is arithmetic series. So this adds up to order of n squared. Then divide, cancel 1 order of n here. So this whole thing gives me still linear expected running time in this case. Okay, all right, questions? Okay, so so this is, I have the derivation here as well. Well, now I want you to, offline, you can compare what we did, this randomized algorithm with the previous linear search algorithm where we did the probabilistic analysis, okay? There we have to assume what the input could be like. Here, I don't have any assumption on A, okay? However, even if you give me, so for example, suppose you give me an array A, okay? Where the key you're looking for, so you have an array n of size n, okay? Let's say that you're looking for key equal to 100. And let's say that in your input array, you are not lucky. This 100 is the last entry in your input array. Okay? Now, using the previous approach, when you run your linear search algorithm to search for 100 in this array, you have to linearly scan through all n positions till you find 100. So then in using the previous linear search algorithm, your time for the specific input is exactly order of n, okay? Because you have to scan through the entire array, okay? So this is a bad input for the previous one, okay? However, now in our new randomized algorithm, the first step, even though your input looks bad, but then the first step is randomly permutes the array. So after that, this 100 can land up anywhere. So it can land up any position with probability 1 over n. It's no longer necessarily bad. Okay, it could be even lucky. It lands in the first position, then the time is only constant. Okay, that's why we have to talk about the expected running time, because there are many possible choices. Okay, so that's a difference between a randomized algorithm and algorithm where you're just doing probabilistic analysis. Okay, so it's important to remember that a randomized algorithm is not deterministic. Namely, even when you have the same input, when you run it multiple times, your running time is different. Okay, what we're really computing the expected running time is basically that when you average all these different runs, what is the expected time, basically. Okay. All right. Okay, so now let's, before we talk about this a little bit more formally, okay, let me just review the expectation, which itself, of course, in statistical data analysis that we use this tool often, okay? So just some simple facts and then see how does that apply to when we analyze a randomized algorithm. Okay. All right, so the basic concept is that if you have X, which is a random variable, okay, and this random variable, the expectation of X is simply computed that what are the values that X can take, multiply with the probability that X takes that value, okay, and then you sum it up. That's expectation. Okay, so a simple example is you have a coin, and let's say it's a so-called a fair coin, which means that if you flip it, then with half chance, you get a head, and with half chance, you get a tail. Okay, so now let's say that we have a coin, and when we flip it, we get the X represents the coin flip. Okay, and what are the choices? Well, we say X equal to 1 if it's a head when we just flip it. okay? And x equal to 0 if it's tail. Okay, so this random variable in this case has two values, 1 or 0, let's say. Okay, and let's say your coin is a very well-made, balanced coin, so it's a fair coin, which means the probability that we get head is 1/2, which also means that the probability we get a tail is 1 minus the probability we get a head, which is also 1/2. Okay, so what's the expected value of this coin flip? Well, this variable x, well, we have equal to, now we need to take what's a possible value of x and its probability. In this case, the value of x can be 1 or 0. So we need to do that. The first case is that the 1x is 1, which namely it's a head, times the value of x, which is 1, plus the second case is that the 1x is 0. Multiply the value of x in that case, which is 0. In this case, it happened to be 0. That's why this term will then disappear. So what we get is simply the probability of x equal to 1 in this case, which is 1/2. So expected value of x is 1/2, because half of the chance that can be 1, half of the chance that can be 0. Expectation is 1/2. Okay? All right. Now, the important property of expectation that we're going to use in analyzing the algorithm will be the following, okay? Number one is the linearity of expectation, which means that if you have two random variables, then expectation of the sum of them can actually be computed by first computing the expectation of each of them and then sum it up. We're going to see in a minute what does this mean when we analyze the time complex of an algorithm. Okay, so that's the first property, fundamental property of expectation that's useful. The second property is so-called conditional expectation. Okay, so you want to compute the expectation of a random variable x. Okay, then you say that, all right, if event y happens, okay, so if event y happens, then if I know what's expectation of your variable, one event conditioned on that y happens, okay? If we also know that the expectation of x, y didn't happen, then the total expectation is simply that what's the expectation of x when y happens, multiply with the probability that y happen, plus the expectation of x when y does not happen, multiply this is the probability of not y. Okay, multiply with the probability when y doesn't happen. Okay, so intuitively, why is this useful? Basically, when your algorithm has case analysis. Okay, so that's basically when something happens, then you do action 1, and when it doesn't happen, you do action 2. Here, the basic tells us that you can use this as the conditional expectation to compute the final time. Okay, so more precisely, let's look at some simple artificial example just to make the point. Okay, so here in this is a pseudocode here. Okay, it's an artificial one because I just want to show how this linearity of expectation can be used. Okay, let's say you have an algorithm. Okay, and the algorithm does the following. Inside your algorithm, then you call another procedure. Okay, so it's just something else that you need to do. Okay, and let's assume that a randomized, namely inside the function 2, I have randomness. Say I have some random permutation or whatever. Okay, I have randomness. Okay, so how do I compute the time for A? Well, first, in fact, before we go to the expected running time, so if we look at the worst case time, okay, I hope it's not too hard to convince ourselves saying that the worst case time for this is for function 1. Okay, because inside I have to perform 4 basically line 4 n times. Okay, so the worst case is that function 2 also have the worst case. So this is actually the worst case, where this is the worst case running time for function 2. Okay, all right, so this is the standard worst case analysis. All right, now for the expected running time, okay, we basically, what do we know? We are basically running this one. You can think that the running time is that the running time for line 4, the first time we run it called x1, the first time we run line 4, the times x1, the second time we run line 4 is x2, and so on, okay? And our total time complexity, expected time for function 1 is simply basically the running time for first time call this plus second time call. Oops, sorry, let me just rewrite it here. The expected time is basically expected time, where inside we first time call function 2 plus the time for second time call function 2 plus third time call function 2 plus the nth time function 2. Okay, and we just said that by linearity of expectation, the expectation of this whole thing equal to that you simply find the expectation of each individual one and sum it up. So this is same as expected time for first call of function 2 plus second call of function 2 plus in the end the nth call of function 2. Okay, now if we assume that ET2 stands for the expected running time for function 2, what we have here is simply that, because I'm calling this one n times. So this is the same as n times ET2 of n. Okay, so that's this is a very simple thing of using linearity of expectation. Okay, so this is what I just stated. Okay, I should also add a C of n because this other lines also take a linear time. Okay, all right. Maybe let me give a simpler the description of what I just said. What this says is that if you have a simple function where inside it calls bar 1, bar 2, okay? So what is so inside this function you call this subroutines, okay? So what is the time, expected time for the main function? Well, that's simply you take each of them and take their expected time and sum it up. Okay, just like a worst case, you can sum up the running time because you say what is the expected time for this and what's the expected time for this, and then you add it up. Okay, so this is simply the ET of bar 1. Okay, now we will use it without thinking much, but this is just to show that this is why we can just add up the expected time of each of the procedure and then sum them up. Okay, so that's the first, the use of linearity of expectation. Okay, the second one, the conditional expectation. Why is it useful? Now consider this artificial pseudocode where at the beginning I flip a random coin. Okay, I flip a coin, and then what my algorithm does depends on what's the outcome of the coin. Okay, if the coin shows heads, then I call a function procedure 2, but otherwise I call another function, function 3. Okay, And assume that we know the expected running time of this two function. How can we get expected time for the main function, function 1? Okay, well, what we have here is that using the conditional expectation, the running time of this algorithm basically is that basically it depends on whether when you flip the coin, the head happens or not, right? So we know that if the head happens, then I need to look at the expected time when you get a head, okay? And then you multiply this expected time with the probability that head happened. Or it can be the second case. If it goes to the second case, what's expect time? What you first say, what is expect time when it's tail? Then with the probability, the second case happen. That's what we have, okay? And if your coin is fair, let's say that with probability 1/2, you get head or otherwise tail, then this, we already said that the expected time when head happen is that you simply go to function 2. So that's function ET of 2, okay? So you get with 1/2 chance, you have, and then with another 1/2 chance, you have ET of 3. That's the expected time of the entire algorithm. Okay, I should be more precise. Is that other than doing this, the remainder function take constant time. So that's what we're adding here. Okay. All right. Okay, so both of these are rather intuitive, but this basically says that when we analyze the helps, when we're given the randomized algorithm, help us to break it down into small pieces and then assemble it to get the expected running time of the entire algorithm. Okay, so these are the two typical cases we see. Okay. All right, so what I want to do now is that I want to just give you a couple of examples. Again, I'm using more artificial examples, but later in this class, when we talk about sorting and select, we're going to show a real randomized algorithm, okay, as well as what's the intuition behind there, why it helps, okay? Okay, so let's first look at this example. So inside, I have a function, I call it random. What the random does is that it basically return a number k out of from one. It basically pick one number from 1, 2, 3, all the way to n. They pick a random number out and return it as a k. Okay, and this is the probability you pick each of this number is uniformly equally, which means that you the probability that you pick the ith number from 1 to n is 1 over n. It's the same. Okay, so you return random number from 1 to n. Okay, in your homework, you also the homework problem also have this, but I think there we're using the Python code, so we're calling this a slightly different name. Okay, but you will see in the description of the problem. Okay, all right. So let's see. This is our algorithm. Before we look at the expected running time, let's first look at the worst case running time of this algorithm. Okay, so I think this is the worst case. So I'll stay on this page so you can see the pseudocode. So okay, let's always call worst case. I use T of n to represent that. Well, this takes constant time. Okay. Okay, then we come to this for loop. Okay, now note that the for loop is a nested loop. And what is the inner running time of this for loop? Note that this is basically constant times the number of iterations here. But this number of iteration actually depends on k, the value of k. Okay, so what we figure out is that this part runs in constant times k time. And the outer loop also have k iteration, which means that the entire for loop takes time constant times k squared. Okay, so this is the precise running time of this algorithm when k is returned in line 2. Okay, when we ask what is the worst case running time, then you say that, okay, how bad can this be? Okay, so I know my running time is ck squared, but the k coming from line 2 could be equal to 0, 1, 2, and all the way to n. Okay, so the worst case running time for this running time is that when k is as large as possible. Okay, so that basically the worst case, let me just write it here. Worst case happens when the choice of k equal to n, and the running time in that case is order of n squared. Okay, so this is what we have. Okay, so that's the worst case running time. All right, so let me clear it. And this is what I showed here. Okay, so again, remember that this happens when k in line 2 is n. Okay, okay, let's now look at the expected running time of this algorithm. Okay, how do we analyze the expected running time? Well, what you want to do is that usually follow the following, you follow the 3 steps. Okay, first you want to identify all possible different cases that could happen for the running time of your algorithm. Okay, then you compute the probability of each of this case, and then you find out the running time of each case. Then you use this formulation, which is that the total expected running time equal to what is the running time of each specific case multiplied by its probability and then summed up. Okay, you essentially sum up all the cases, running time of all possible cases, weighted by the probability that they're happening. Okay, so this is the standard 3 steps. Oops. Okay. Now, for the previous example code, let's see what are the different possible cases. Okay, we have here that we already figured out that just now the running time here really depends on the choice of what your value of k is. The running time was ck squared. Okay, what choices do we have? Well, k could be 1, 2, 3 till n as returned here. Okay, so we figured out that there are altogether n possible cases for the running time. Okay, and those depends on what k is after step 2, line 2. Okay, so that's the first thing we figured out here. Okay, so we identify that all the possible cases, we figure out that there are n cases depending on what is the value of k. Okay, k could be 1 till n. Okay, okay. The second step is that what is the probability of each case? Okay, so we said that each case is at k equal to a specific value in I. So the probability that, so now it's for step 2, k equal to I, we said that k is a random number from 1 to n, which means that the chance that k equal to a specific number is 1 over n, because there are n choices and I pick 1. Okay, so the choice is 1 over n. Okay, so that's a step 2. Okay, step 3, what is the running time for each of the case? Well, the running time when k equal to I, We already saw it in the previous slide, because the later the loops, the running time depends on k, okay? So if k equal to I, the time was c times k square is proportional to k square. So if k equal to I, then the time is simply c times I square. Okay, so this is what we have for step 3. That's the running time of each of the case. Okay, how do we put all of this together? Well, we now have the final expected running time of this algorithm equal to the summation of what is the running time of each case. In this case, k could be equal to I. And what how many cases do I have? Well, I could go from 1 to n minus 1. Each number is equally likely, okay? Times the probability that this is happening. Okay, by expectation, you basically said that I'm summing up all the possible time, all the cases, the running time of them weighted by the chance they're happening. Okay, and now from step 2 and step 3, we plug them in. We have the probability this happens is 1 over n. And when it happens, the time is ci squared. So what we got is c over n. I'm taking this out of the summation. Summation I equal to 0 n minus 1 I squared. Okay, now you can use a precise formula, or we also summarized last time that the summation of I to the d, for I goes from 0 to n or n minus 1, is actually big theta of I to the power of d plus 1. So the summation of I squared, basically this is the same as 1 square plus 2 square all the way up to n minus 1 square. Okay, this turned out to be big theta of n cubed. Okay, all right. So as such, we know that this is n cubed. We know that this is n cubed, and n cubed times c over n, where n, one of the n factor cancels, we have as such big theta of n squared. Okay, so in this particular case, just to summarize with what I just said, this is the calculation we have. So in this particular case, the expected running time asymptotically is actually the same as the worst case. Okay, although the truth is that the constant involved are different. Okay, but asymptotic time complex don't see that. So expected running time is still quadratic. We're not asymptotically, we're not saving much by doing this, having this randomness in the code. Okay, questions? Okay, now let's look at another similar example, but where this did matter. Okay, so it's very similar to the previous one, where in the function first, what we do is that we pick a random number from 1 to n. Okay, that's what this is doing. So k is a random number from 1 to n. Okay, then after that, we do the following. Okay, if this value of k is smaller than log n, then we compute this. Okay, so this part, the running time clearly is cn. Okay, but we'll only run this little code when the value of k is smaller than log n. Okay, otherwise, if k is bigger than log n, we do nothing. Okay, all right, let's see that. First, what is the worst case running time of this? Okay, we said that the worst case now, basically the running time depends on the choice of k. So you need to figure out for what choice of k is the function runs slowest. Okay, the running time is the biggest, basically. Okay, so you want to look at the worst case. Okay, now we see, okay, k can go from 1 to n. And we figured out if the k is bigger than log n, then that's the best case, because if k is bigger than log n, then the algorithm does nothing, so it's only constant. Okay, but if k is smaller than log m, then you have to run this linear time subroutine. Okay, so the worst case happens when k is smaller than log m. Okay, and in that case, in that scenario, I have to run the code from line 4 to 6. So the running time in that case is c times m, which is linear. Okay, so this is the worst case time complexity of this algorithm. Okay, all right. Now, I'm just summarizing it here. Let's now see what is expected running time of this code, okay, of this algorithm. So remember, what are the steps? The steps is that first you need to figure out, okay, step 1, what are the different cases of the execution of your algorithm, okay? Well, here actually the situation is easier. I have only 2 cases. When I get a random number k, depends whether k is smaller than log n or not. If it's smaller, I do one thing. If it's bigger, I do another thing. Okay, so there are only 2 cases. So we figure out we have 2 cases. K smaller than or equal to log n, or k bigger than log n. That's what we figure out for step 1. Okay. Step 2. What's the probability of each of the case? Okay. Well, let's see. I have 2 cases. The probability that k is smaller than log m is, what do you think? So k, you have 1, 2, all the way till m, and the k can be any one of them, right? So the chance that k is smaller than log m is basically means that k could be 1, 2, all the way till up log m. So there are log n choices for me for this to happen, for this condition to hold. Okay, there are altogether n choices. Log n out of them will be good for this condition to hold. Okay, so the probability is simply log m over n, because I have n choices. For log n of those choices, this holds. This is true. Okay, so that's a probability. And what's the probability that otherwise? Well, that's the same as 1 minus the previous probability, which is so this is the step 2, what we have. Okay, so now we know there are 2 cases and we know the probability of each of the cases. Okay, let's see what is step 3. So in step 3, I need to know the running time for each case. Well, we have 2 cases. The time for 1k happen to be smaller than log m. Well, if k is smaller than log n, we have to go to the code and execute the lines 4 to 6. So that's cn time. Okay, so that equal to basically linear. Okay, and if k is bigger than log n, what do I have? Well, if k is bigger than log n, we don't do anything. We just immediately return. So we do nothing. So the whole time is basically constant for all the other steps in this algorithm. Okay, so this is just a constant c prime called. Okay, so that's what we have. So now we're ready to get the final expected running time. So the expected running time of this algorithm equals to the probability that k is smaller than log n times the time for k smaller than log m plus, let me erase this just so I have the space, plus the probability that the second case, which is a k bigger than log m, times multiplied with the time of k bigger than log m. Plugging everything that we already know, this probability is log n over n, in which case we take Cn, linear time. Then we have this probability is 1 minus log n over n multiplied with some constant. Okay? All right. The first one, n cancels. Okay? Which means that we basically get Cn log m. And the second one, this, we don't exactly know what is log n over n, but I don't care because I know that 1 minus this has to be smaller than 1, so it's still a constant. Okay, so the whole thing as such is only log n because this is a dominating term. Okay, all right. Okay, so this is what I said is summarized here from all the 3 steps. Okay, this is final time complexity analysis. Okay, so this is just the what we just went through. Okay, all right. Okay, as I mentioned, this example is rather artificial because here I really try to, so in this case, what we see is that the worst case running time is linear, okay, but the expected running time is only log n. So the difference between log n and n is huge, okay, just see the difference. Versus n, okay, just to have an idea of the difference. Imagine your n is really large, okay, your n, let's say, is 1 billion, okay, 1 billion is roughly 2 to the power of 30, okay, so this is roughly 1 billion. Okay, so if you have an algorithm that runs in linear time, you basically need 1 billion operations. Okay, but if you have log n in that case for 2 to the 30, then this is same as 30 times log 2 because the exponent goes to the front. And suppose it's base 2, let's say that we actually do base 2, just make it simple. Then log 2 base 2 is 1. So then you only need 30 operations versus the 1 billion. Okay, so the difference between log n and n is huge. Log n is much, in some sense, much closer kind of to constant. Okay, the reason is because that essentially to get n is actually by definition, okay, log n happens in the exponent. Okay, because some remember that the log a n essentially is at a to the power of this equal to n. Okay, so this is the how many times you have to multiply the base to get n. So this comes in the exponent. Okay, so the expected running time and worst case running time of the previous artificial algorithm is huge. All right, and when we talk about the select order statistics, we're going to see a real randomized algorithm, which also improves the time complexity dramatically. Okay, all right. Okay, so in the remainder time, let me say a few words also about the lower bound. So far, given an algorithm, we have been focusing on talking about that's the running time that what is the, whether it's worst case, best case, or average case, what the running time is. Okay, now suppose you're given an algorithm. Okay, if suppose you are given the problem. Okay, we can come up with many different algorithms. Okay, and some of them have better time complexity than others. Okay, let's say that later when we talk about sorting, a naive algorithm would take a quadratic running time, and then someone else had a more intelligent design. Turns out the running time is only n log n, which is much better than the quadratic running time. Okay, but then the question is that, can you do even better? Okay, say for sorting, can you do, we suppose we have an algorithm which is n log n, can we do even say linear? Can we do even better than that? Okay, so given the problem, what is the best possible running time, time complexity for that? Okay, so this is this kind of questions intuitively are very hard to answer, but it's important question because if you know that sorting cannot be done by any algorithm in time n log n, what does it mean? That means that don't even try to get a linear time algorithm for sorting, because I mean there's already a result saying that no algorithm can run better than n log n. Okay, but the question is usually hard to answer because, I mean, naively, how should we know for sure no better algorithm exists? We have to know, we have to enumerate all possible algorithms, says that none of them run faster than, say, n log n. Okay. So sometimes, very often, what we aim is just to provide some lower bounds, saying that this algorithm, this problem definitely cannot be solved better than a specific time complexity. Okay. So a simple example would be, a simple and a naive example would be that you given an algorithm, a problem, say sorting, okay? The following statement would be true. I said that no algorithm to sort a list of n numbers can be better than constant running time, because at least you have to load your array and so on, okay? So this is the correct statement, and this constant running time is a so-called lower bound, because I said that any algorithm for sorting has to at least be bigger than this, than constant. Okay, that's why it's called a lower bound. Okay, so this is a valid lower bound for the sorting problem. Constant is a valid lower bound for sorting. Of course, in this case, it's a very boring lower bound and not very meaningful. Okay, all right. So slightly more precisely, okay, we say that f of n is a theoretical lower bound for a specific problem, okay, if every possible algorithm for that problem, the worst case time complexity is at least f of n. Okay, so again, what I just, this silly example I give just now is that the sorting problem has as a theoretical lower bound. So this is a correct statement. Okay, not very useful though. Okay, all right. Now here, just let's look at the search problem that we have seen before. We're given an array. We try to search for a specific key k, whether it's inside or not. Okay, again, for the search problem, I can give the same constant lower bound, because I mean any algorithm has to at least do something to this array, at least need to return something, so that takes constant time. Okay, so this is not wrong, it's just not useful. Okay, on the other hand, if you think, how do we convince that we have a better lower bound? Well, if we're given an arbitrary array, we know nothing about it, okay, of size n, and you give me a specific key k, okay, you can see that in the worst case, okay, any algorithm has to touch each entry in the array at least once to see whether that entry is k or not, right? Because if you only visit half of the entries and didn't look at the remainder, and you say that, okay, the key is not in, then how do we know for sure the key k is not in the remainder half that you didn't see? Okay, so of course, if we know nothing about the input array, okay, then we have to, unfortunately, in the worst case, check all entries inside. Of course, it can be lucky that when we check the first one, we already found it. So that's a good case. But in the worst case, we're not lucky. Then we have to prepare for the worst, where we have to check every element inside. Okay, so as a result, what I just said is that the lower bound for the search problem is linear. okay, a big omega of n. Namely, any algorithm in the worst case need to take at least linear time, okay, because we have to inspect every element in A. Okay. Now, I want to emphasize here, I meant that we're given an arbitrary array and we don't have any other structure associated with it. If your input array sorted, has structure and has some prior knowledge, or you know your input array actually can only contain 2 elements repeated, 0 or 1, then become very easy. You have prior knowledge, okay? But suppose you don't know anything and the input array can be anything, then it takes at least a linear time to solve this problem. Okay, so as such, the search problem has a theoretical lower bound, which is big omega of n, which is linear. Okay, now this is a good lower bound. Why is this good? Can we get even higher? So lower bound, clearly, the higher value function is, the bigger the function is, the harder it is to get, because I can always trivially just give you constant. Okay, so you cannot go any higher of this because we already know that for the linear search problem, we already know that for the search problem, we give a linear search algorithm, which is the running time, the worst case running time is exactly linear, okay? Which means that that linear search algorithm of before is in some sense optimal, okay? Because you know any algorithm for search problem takes at least linear, and then that algorithm takes linear, which means it cannot do better. That's the fastest possible for the doing search to certain element in the array. Okay, and in this case, if you have an algorithm to match this lower bound, okay, we say that this lower bound is tight, or we sometimes say that this is optimal. Okay, so in other words, you have a lower bound, and now you found some algorithm actually can really achieve this, solving the problem using this lower bound, which means that that algorithm has to be optimal because it cannot be any faster. Okay, so that algorithm is optimal and your lower bound is tight. Okay, but most often in practice, for many problems, unfortunately, lower bound is not so easy. Okay, while upper bound is easy, because for upper bound, if you just come up with an algorithm, then the time complexity of an algorithm will be an upper bound. Okay, you just don't know whether you can do better or not. Okay, so very often in practice, sometimes you hear people say that, oh, there's a gap. The best algorithm we ever developed for this problem is n log n, but the best lower bound we can find is only linear. We don't know whether there's a better algorithm. Okay, so in other words, imagine the situation where, say for problem, for problem P, okay, let's say that the Alex given the algorithm that runs in n log n time, okay? And let's say that, let's say Julia showed that there's a lower bound for this problem. Okay, what do we know combining these two? What we know is that any algorithm, the best possible algorithm, the best possible algorithm's running time is at least linear, and we know that the best possible is at most, sorry, I should use at most, I should use big O of n log n, because we already know n log n can be achieved, but we don't know whether there's a better one, but we know it cannot be better than linear, okay? So that means that the best possible algorithm the running time has to lie in between these two, although we still are not sure, okay? The way usually to close the gap is that either but if you don't know whether you have a matching lower bound or not, that gives you hope that there may be a matching lower bound, so you can try to design a better algorithm, okay? All right. So this is what we just set. Okay. All right, I think today, that's all for today. I think I'll stop here because next time we're going to start a new topic. We're going to talk about binary search in sorted array, okay? So that's all for today.